with it or don't like it, because there isn't just one way to do things. And oftentimes it takes tenacity. Tenacity, it takes grit. Sometimes you'll do a whole lot of work and realize you've gone terribly wrong and you have to start again. So a lot of people find this unit frustrating for that reason, that you get so far down a rabbit hole and you realize that this isn't going anywhere and you've got to try a different strategy. It's also about having more than one strategy as well, which is difficult when you're seeing it for the first time. I'm sure I told you guys this story. I did an answer key for a test. I think mine was 12 lines, and a kid brought up their test, marked it. It was 100% correct, and they did their answer in three lines. So, I mean, that's amazing, and I like it because I get to see how you guys think. But the thing here is it has to be mathematically sound, and it has to be equivalent in value. So all those things have to be in place. You can't make math magic. You can't just magically take stuff away. So you need to be strong in your operations. We'll say that. Okay, we're going to be checking a lot of left-hand side, right-hand side. So we're going to be talking about things. Identities are things that are mathematically true. You don't have to prove them. You know that they're true. You guys don't have to prove a squared plus b squared equals c squared every time we use it, right? You guys trust that Pythagoras had a good understanding of it. Maybe you proved it back in elementary school, but you don't have to prove it every time. So trig identities are things that we know, or mathematical identities are things that we know are true, that are absolutely true. You don't have to keep proving them over and over again. Okay, so reciprocal identities, you guys already know these ones. We've already done reciprocal identity. Well, we've already done reciprocal functions in the trig unit. So cotan is a reciprocal function of tan. So cotan is equal to 1 over tan theta. Pretty straightforward, right? Easy peasy. What's the other one? Tan is the only one that has a different, has two. Okay, maybe let me back up. Tan theta is equal to sine theta over cos theta, right? Everybody knows that? So that's also another identity. Tan is its own, oh look, quotient identity is right here. Let me fill this one in since we're already skipping ahead. So sine is cos over theta. So what would cotan be? Yep. So cos theta over sine theta. So it's the reciprocal of it, right? It's going to flip. What is the reciprocal function of cosecant? 1 over sine. Yep, cosecant and sine. I also noticed we tend to get, I don't want to say lazy, but we tend to rush and we're forgetting our thetas. We'll say 1 over sine. That is a deduction of half mark every time. Okay? So if you're losing your theta or your x or whatever that angle is, you can't just have sine on its own. It has to be sine of an angle. So that variable has to represent the angle. It has to be there. And secant is going to be 1 over cos theta. Easy peasy, right? You guys all know those. Those you can do in your sleep. Okay. Do you guys remember Pythagoras? We just talked about him. What's Pythagoras' rule? All right. Now we applied this. You already saw this for the equation of the unit circle. Do you guys remember that? We did. Right? Remember we did that for the unit circle? We did. If you don't remember, we did. Hypotenuse being 1 on the unit circle. What trig ratio is x? Cosine. And what's y? So that's just that. So what we've done is we've taken Pythagorean's general identity, we applied it to the unit circle, and then we applied it to our trig ratios. So all of these are equivalent. They're mathematical truth. We don't need to do anything. We don't need to prove them every time. It's just there. But I did 3 substitutions of things I know to be true. And on your formula sheet, that Pythagorean identity is your very first one. Now they have sine squared first, and I put cos squared first. It doesn't matter when you're adding. These order can be rearranged. Pretty exciting stuff right there, eh? So if you notice, so we're going to do in chapter 6, we're going to do all of these, all of these, all of these, and all of those. So really that first column on your formula sheet is chapter 6. Logarithm functions, chapter 8, and permutations and combinations, and binomial expansion is chapter 11. And really, and so ladies and gentlemen, like, and there's your quadratic, and there is your arc length. And that's really it on your formula sheet that you get. Everything else you have to store in your brain. Okay. I want you to take the Pythagorean identity, and I want you to use this one, and I want you to divide all terms by cos squared theta. Do it. Go. Divide all terms by cos squared theta. And I can do this. This is mathematically sound because I'm dividing all terms. All terms. I can't divide just one because that's not going to be equivalent statements. So what's cos squared divided by cos squared? Good job, everybody. What's sine squared divided by cos squared? Tan squared. And what's 1 divided by cos squared? Secant squared. That is the second identity on your formula sheet. You've just proven it. So really, that's just the Pythagorean identity, and we've rearranged it, and we've made it look a little bit different, but there's nothing mathematically that this and this are equivalent. We've done the cos squared on all the sides. If we do it by sine squared again, so we're going to have cos squared theta plus sine squared theta equals 1. That's my Pythagorean identity. This one is one of the most useful ones that you're going to use. So it's really, this one's going to be super useful in solving identities that we're going to do in 6.3. So if we divide all this by sine squared theta, so now this one is cotan squared theta plus 1 equals cosecant squared theta. And I know I haven't reiterated it, well, I've reiterated it before, but this is the same thing, mathematically speaking, as that. Like this and this are the same thing. Like mathematically, we do it like this. We do cotan of the angle, and then we'd square that result. You can't just square that, but we write it like this. And I find that a little bit confusing because mathematically we're doing this. Okay, so you've just done 3 identities. This is another one that's super helpful. I'm going to take this and I'm going to do this to it. All I did was take the sine, or take the cosine to the other side. So sine squared theta is equal to 1 minus cos squared theta. And that's going to be helpful too. And the reverse of that is going to be cos squared theta is equal to 1 minus sine squared theta. I'm also going to point out something else. Can you factor that? That's a difference of squares. Perfect square in the front, perfect square in the back. Oops. So all of a sudden, I've taken a really generic, like this is my Pythagorean identity. I've taken a really generic thing and I've made 4 or 5 or 6 different identities out of it. So you know all this stuff, but are you comfortable enough with it to see it in different forms and use those different forms to help you? And this would also be a difference of squares too, right? Because a perfect square in the front, a perfect square in the back. Notice that there's no squareds on here. So your Pythagorean identity is going to be one of the most helpful ones because it's one of the most easily manipulated identities. So, I mean, do with that what you will. I'm telling you that these are things that you need to know. So this is given to you on your formula sheet, but you could do this, you could do this, you could do a factor situation. This one's given on your formula sheet, and this one's given on your formula sheet. Are these difference of squares? Could I factor these ones? No, they don't have it. It's not subtracted, right? So I can't factor this one and I can't factor this one. I can factor these ones because they have the subtract sign in them. So it's about understanding. Like we did difference of squares back in grade 10. And we're looking at it in a very, very different way. Okay, so that's your Pythagorean identity. Like I said, one of the most useful ones because it's the one we manipulate the most. Are you guys okay if I flip the page on this? All right. So we're going to use some identities to do some basic simplifying. Super easy. So right here, we can't simplify anything. But if we substitute something else in, we can then go ahead and simplify. So which one? Cos is a basic trig function. Cos and sine are basic trig functions. They're not going to simplify anymore. That's where it stops. But tan we can replace. What can we replace tan with? Sine over cos, yeah. So we would do sine theta over cos theta multiplied by cos theta. So what's going to happen to those cos thetas? They're going to cancel. So that simplifies to sine theta. Now, again, given as an expression, my answer should be an expression. There should be no equal signs in there as well. We're going to take chapter 6 and we're going to get really good at our notation. Okay, this one's a big one. This happens all the time. Express tan squared theta in terms of sine theta. So what I want, they can be sine squared, it can be a regular sine, it can be 1 over sine, but all the answer can have in it is the sine function. Okay, everybody with me here? So what do we know? We know that tan squared is sine squared theta over cos squared theta. Right? Would you guys agree with that? Can I leave it like this? Because what is the only thing I can have in my answer? Sine. Okay. So, top's good. Great. I got to work on that cos squared theta. Is there anything that we just did on that first page that I could replace cos squared theta with? The Pythagorean identity rearranged. So I'm going to replace this with 1 minus sine squared theta. And this you'll see on tests and quizzes where I ask you to take a trig expression and change it so it's only expressed in one trig ratio. So this is it. Like if you went tan squared theta and you went right to cotan, I'm not sure what I would do with cotan, but I could work with cotan a little bit. I could use this because this is a reciprocal function, but I've got that plus 1 in there. So there's still some things I can work with here. So it's about manipulating and changing things. All right, non-permissible values, our favorite thing to do. We've got hidden non-permissible values and we have straight up non-permissible values. There's a hidden non-permissible value in here. What is that? What? Yeah. Simplify, I'm not going to say simplify because we don't want to cancel anything out. You remember, factor everything, do NPVs, then cancel stuff out, then simplify. So this would be 1 over tan x. And we can leave this as cosecant x, and we can leave that as cos x if we want. All that's fine. I just wanted to show you the hidden non-permissible value because if I have an undefined on tan in the numerator, then we're going to have a problem for that whole fraction. Okay, so let's deal with that hidden NPV. Yeah. Yeah, we can totally do that. We're going to do the hidden one first, and then we're going to do the other ones. Do you guys, I don't know if I have my sheet. Radical functions. Oh, look at that, sinusoidal functions. Right here, it's almost like I planned it. Tan graphs, you guys remember those? Tan graphs? So where is tan equal, like where can tan not be 0? Pi over 2, right? So we know that our first asymptote on our tan graph is at pi over 2, so that's where it would be undefined. That's where we would have our asymptotes. Everybody good with that? But really, maybe it might be better to look at the cosecant graph. Or sorry, cotan graph. Do you guys remember the cotan graph? Why do I not have my cotans in here? Do you guys remember those? No? Nobody remembers? I'm just in this by myself? Okay, I don't know where my notes went.
I have no idea what happened.
All right. Oh, here's one of them. I don't know where the other page went. That's cosecant. I need cotan. So if the asymptotes are at, so tan x is undefined at pi over 2, right? Everybody agree with that? So we know that x cannot equal pi over 2. And do we have any restriction on this? No. So general solution. Okay, so we did that one first. Cosecant. Just by chance, I have my cosecant here. I don't know why, I just have these two and I don't know where secant is. Where's the first place with my asymptotes? Pi or 0, either one will work if you like pi as well. So we're going to do the non-permissible value for cosecant. So the cosecant one will be x cannot equal pi plus, where's my next one? It happens every pi, right? So when I'm doing my general solution, plus pi k, KEI. All right, so let's challenge yourself. I know you haven't had much experience, but can you guys go and try to simplify that expression? So now you're gonna go ahead and cancel stuff out. Oh, guys, cosine. I didn't do the cosine one. I did cosecant. I didn't do cosine. So where is cosine 0? Where's cosine 0? Cosine is 0 at pi over 2 and 3 pi over 2. So that's going to be every pi. Do I need to write that one?
I'm supposed to remember all of it.
Yeah. So that's the knowledge of your unit circle, right? Where is everything 0? Where's tan 0? Where's cos 0? Where's cosecant 0? So you need to know your asymptotes. I'm going to tell you though, I'm going to be completely honest with you, non-permissible values, like if this is a 3-mark question, non-permissible values are probably going to be a half mark on this. So don't lose your mind over non-permissible values, get that 2.5 marks, right? Go from there. Okay, simplify. Go ahead and simplify. Do your best. Try some stuff. I want to see how tenacious you are. I think I did that right. There's lots of ways to do it. Yep. Can I show you my solution? And keep in mind, my solution is not the only solution. There's lots of ways to get to the end answer, but your math has to make sense. And for those of you who like to skip steps or are messy with your math, I need to be able to read all your steps because you need to show me enough so that I see what the math it is that you're doing. And I find people skip through and skip some steps. So the way I tackled this one is I really hate fractions inside of fractions. So I changed it to a divide question. That's all I did for my first step. And I had already simplified, like I'd already kind of changed the numerator, so I just stuck with that. And then I was like, okay, what if I change this into its reciprocal function? So that's 1 over sine. Oh, look at that. If I multiply these, so I haven't done my big division yet. I did cos over sine. And I'm like, hey, that's cotan, that's cotan. Get an answer of 1. You could have worked this with the, you could have gone back to cotan instead of expressing it as 1 over tan x. You could have expressed it as cos over sine x. You could have gone that route where this went automatically to cos over sine x, and then you got there on this side, and they're both the same. Like I said, there's lots of ways you can get there, and I think that's the frustrating part about this unit is that you and the person sitting next to you, your understandings would be different, and that's actually really okay. And sometimes it's really hard for us to see our thinking process and put that down on paper. Okay, if you didn't get a solution, or if you got a solution that was different than mine, your answer still should be 1, but how you got there, is there enough math on the page that I'm going to understand it? All right, determine the non-permissible values in degrees for this equation. Okay, let's do the obvious non-permissible value. Sine? Where's sine 0?
Pi?
Pi, 0, 2 pi, right? So theta cannot equal 0 plus 180 degrees k KEI, right? Because this one asks for degrees. Now let's do the hidden one. Tan is sine theta over cos theta. So what am I looking at now? I'm looking at the cos theta. So where is cos theta 0? 90, and every 180 after that. And then I'm looking at the hidden one in here. That one's going to be 1 over cos theta, but we just did cos theta, so I don't need to rewrite it. So it's not just looking at the specific denominator of like, oh, sine and I'm done. You got to look for those hidden denominators too in those reciprocal functions. Are we good with that? Okay, easy peasy. All right, so there's mathematical proofs and there's verifying. Mathematical proof, an identity is through a proof. If you're doing a mathematical proof, it means it's true for all values. So proof a proof is good for all values. Verify is only good for a single value. So when we ask you to verify something, you're verifying that when theta is 60 degrees, the equation is true. When you're doing a mathematical proof, what you're doing is you're proving it's true over all values. So those are two different things. We're going to do proofs in 6.3. It's definitely my favorite lesson and my favorite unit. Yeah. Okay. So let's dive into this. We got 2 to do. We're going to do a verify. So we are verifying at 60 degrees. So we're going to use that equation before. So it is secant of 60 degrees is equal to tan of 60 divided by sine of 60 degrees. Okay, so we need to know stuff about our unit circle. It might be helpful, I'm just going to slide up here for a sec. It might be helpful. 60 degrees, would you guys agree that that's up there? Right? 30 would be here, 45 would be here, halfway. So we're going to say that that's at 60 degrees. What are the coordinates at 60 degrees? Yeah. It's a short long. It's a 1/2 and a root 3 over 2. So you thought you got away from chapter 4, but you really didn't. It is here. So you need to know that in order to do this question. All right, so if we know that for 60, We can do a lot of things with that information. We know the value of secant 60. Secant is the reciprocal function of cos. So that means we're taking the cos value and we're just flipping it upside down. So that's going to be 2. Oh, sorry. Sine of 60, you guys know, is the y value. So that's going to be root 3 over 2. Now we need to know tan here. So again, if you don't have it all memorized, you can math it out. You guys know that tan is sine divided by cosine. So if I go up here, I'm going to go root 3 over 2 divided by 1 over 2. So root 3 over 2 multiplied by 2 over 1. So we know that tan of 60 is root 3. So this is why it's handy to know the values. Some of you have already memorized tan and you knew it was root 3, so you didn't need to do that math. Some of you didn't need to draw the picture to know where that coordinate was. We're all on different journeys of our memory here. I really hate fractions and fractions, so I like to write it as a divide question. I'm going to go down here. I'm just debating where I'm going to write it. So we verified that this equation is true over at 60 degrees. That's all we know. That's all we know is at 60 degrees it works. Okay, so let's do pi over 4 now. So we're going to do secant at pi over 4 equals tan of pi over 4 over sine of pi over 4. All right, what do we know about pi over 4s? We know the x and y are the exact same. Do we remember what those values were? You guys can't answer. Anybody else? Anybody else remember? Root 2 over 2. Sorry, you guys are just nailing every question. You got the unit circle memorized. So we know that at pi over 4s, the x and y are the same value, root 2 over 2. So we know that secant is the reciprocal of it. What do we know about tan at pi over 4 if the x and y are the same value? 1. If something is divided by itself, it's going to be 1. Okay, so I got 2 over root 2 equals 1 divided by root 2 over 2. I wouldn't rationalize any denominators unless it specifically asks you to. I will tell you that that is not a thing on the provincial exam to rationalize denominators. You totally can if you want to, but if you screw up, I got to deduct your marks. So I wouldn't touch it unless it specifically asks you to. You need to be able to identify that 1 over root 2 is the exact same thing as root 2 over 2. That's why rationalizing denominators is important, to see the equivalence of them. Okay, I'm not going to do the C part, but we're just going to talk about it for a second. If I were to use technology to decide whether these equations would be an identity, if they would be a proof over the domain negative 360 to positive 360, how would I do it? I would treat it as the 2 equations. I would graph one equation as y equals secant theta and y equals tan theta divided by sine theta. I'd graph these two and see if they lay directly over top of each other. That's how I do it graphically. You're not going to be asked to do that, but that's how I would attack it if that was a question that was asked. We're not gonna graph hardly anything in this unit. So we get to take a break from graphing. That's good. Okay, so that's that. So remember when we're asked to verify, we're proving it's true for that specific value. All right, here we go. Okay, so we know, I'm just gonna move this over here for a sec. Cotan squared pi over 6 plus 1 equals cosecant squared of pi over 6. I like to put my angles in brackets. I don't know what that is, but I just like to do that because I find too many run-on things makes my brain a little wonky. I've gotten into the habit when I'm doing trig identities to do this stuff off on the side. Like, so if I'm going to do sine of pi over 6, if you look at your unit circle, that's 30 degrees, that's down here. So sine of pi over 6, what's the y value? It's a short, so it's going to be 1/2. And cos pi over 6 is root 3 over 2. My x is longer than my y. So that's how I remember it. I remember it that it's a long short or short long. That's how my brain works if I know where I am on the unit circle. So then I'm going to do tan of pi over 6. So 1/2 divided by root 3 over 2. 1 over root 3. Some of you will remember that from the Claudius data table. The smallest angle in tan is going to be the smallest value, which would be 1 over root 3. It's 1 over root 3, 1, and then root 3. You can math all this out, right? But if you're looking for strategies to go quicker, it's going to be that memorization that's going to help you go a little bit faster. So with that information, I know I can answer this question. I've done my basic trig functions off to the side, so now I can fill that stuff in. So cotan of pi over 6. I know that tan of pi over 6 is at 1 over root 3. So what's cotan? Root 3. So it's going to be root 3, and then it's squared. So remember, that's the math that we're doing with that squared piece. Plus 1. Cosecant is the reciprocal function of sine. Sine is 1/2, so that's going to be 2, and that's going to be squared. I forgot my 1. I put the plus sign, forgot to put my 1 in. So what's a square of root 3? Hopefully it's 3. 3 plus 1. 2 squared is 4. 4 equals 4. Is that true? Yeah, so we verified that it works for pi over 6. Okay, so verify is just checking that this 1 point works. All right, crazy kids, you're going to do the next one on your own. It's a 3 pi over 4. So nice, it's a pi over 4, you know something right away, but what quadrant are you in at 3 pi over 4? You're in quadrant 2. So what do we know about the x values in quadrant 2? They're negative. And what does that mean about tan? Tan will also be negative as well. Am I good to show you? Are you still working on it? I still see some heads down. So again, when I'm marking these verify problems, just like the remainder theorem on your chapter 3 test, I'm looking for that your math is the right answer here. It's not just that you got like, so, Rahat gets 1/2 equals a half, and he's verified that it's true. But I don't know where that half came from, like something went wrong in the mathematics there. So they wouldn't get, you wouldn't get full marks for that if these numbers aren't what they should be, right? It's not good enough just to say, yeah, it's verified. It has to be verified with the correct values. And I say that with all the love in my heart because I'm looking for that -1, not a +1. If you put a +1 in here, we all get +1 in the answer, but if you don't substitute the correct value of -1 in there, you're going to be deducted marks because what you've substituted was not the correct value. Okay, that is it for the first lesson. That's a nice easy glide into. I will tell you that all verified questions work. Okay, so if you get a verified question that doesn't work, I've either made a mistake in the question, and I think this book's pretty solid. So go back and check your math or check with me. But yeah, all verified questions should work. I say that with like 98% certainty.